Hi friends, welcome back to LGF. Last time we discussed about the closed loop transfer function and open loop transfer function, right? Open loop transfer function and closed loop transfer function. We have seen some problems also. Now friends, we have seen the transfer function GS in a block. I'm taking like this, applying some input to it, RS, getting some output from the system, CS. So this, the system parameters, we call the transfer function. Is it okay? So this is the simple block diagram in which we are getting only one block contain GS. GS is directly relating the input and output. So GS is our transfer function. But in actual, we will not get the simple one block diagram. We'll get, there is so many block diagrams inside of it, means so many systems. Some systems are connected in cascade, parallel. They are making some loop also, because this is the closed loop control system we are talking about, like this. Okay, so inside of this block we can assume that we'll get this complicated circuit. Is it okay? So what will be our task here? Our task will be to convert this entire complicated circuit in single block diagram or single transfer function. Okay, so we have a need of reduction of this circuit. So by which method we'll do that? We have two methods, block diagram methods and SFG. Okay, first we'll deal this system, given system, whether it's block diagram system or it's SFG system. Okay, so let's start about it. So let me clear it, then we'll discuss about this. Okay, so till now we have discussed the open loop transfer function. It was GS simply. The closed loop transfer function, it was GS 1 plus GS HS, right? If the feedback element is HS. Okay, and if you have HS equal to 1, then your transfer function will be GS. So in this case, GS will be equal to, simply this is the transfer function. Okay, the transfer function will be equal to GS divided by 1 plus GS if you have unity feedback. Okay, then we discuss about the poles and zeros. It was like S minus S1, S minus S2, S minus SA, S minus SB. Okay, so this numerator terms we call the poles and this we call the zeros. Okay, then we have seen the proper, strictly proper and improper transfer function, and we have done some problems. What will be the today's lecture? Today we'll discuss about the calculation of transfer function by these two methods, block diagram and SFG. Okay, we'll discuss about the Mason's gain formula. This one is very important. Entire TF calculation is based on this one only. Then we'll see the gate problems. Okay, so let's start the session. So what is the block diagram? A block diagram of a system is pictorial representation of the functions performed by each components. Okay, so till now we have seen only block diagram representation, in which we'll consider one block. That block will represent the transfer function of individual system. To this we'll apply the input and we'll get the output. So this type of representation is the block diagram representation. Okay, now this block may be in cascade form like this. Let's take it G1, G2 and G3. They are cascaded like this. You are applying input over here, you are getting output from this. In this case, the transfer function will be multiplication of individual transfer functions. Okay, so we have seen this. So in the block diagram representation, or in this technique, we'll encounter with this block diagrams. Is it okay? But what will be there in the SFG? In the signal flow graph, let me clear it first. In the SFG, it is the graphical representation of the relationships between the variables. It will be graphical representation. Okay, I'll show you. It graphically displays the transmission of signal flow through the system. Let's take this example. See over here, for the same system, here we have the block diagram representation, and this is the signal flow representation. Okay, SFG. Now this block over here, if you'll consider the G1 is, we are taking over here by this signal flow only. Okay, so between two nodes, instead of block, we have this branch only in which the signal is flowing, and this will represent the transfer function of this. In the block diagram, for the same node, in between them will have one block, and the transfer function of that block will be G1. Is it okay? So you can see over here, the same system, we are applying input RS. Over here also it's RS, so it's input node, we are getting YS. Here I'm getting YS. Okay, now between this, suppose let's take it 1, over here it's 2, between 1 to 2 we have G1, so it's over here 1 to 2 we have G1, then we have G2, here we have G2 over here, and this is the summing point, sampling point over here, and we are getting YS. Okay, so these two are the equivalent to each other. Okay, now in this entire unit we'll discuss all this block diagram and SFG diagram. We'll solve this. This is the entire complicated circuit. What we have to do, if you have the input and output relationship, you have to make this entire circuit, complicated circuit, in single block diagram, and that single will show the transfer function of it. It will be RS. Over here it will be CS. Okay, so we'll use the Mason's gain formula to solve this circuit. Is it okay? Now let's discuss about let's understand the terminology of SFG, right? See over here, what is the node? It represents the system variable. In the SFG you have seen we have some nodes like this. Okay, here I'm doing one SFG. This is the input node RS, output node YS. In between them, let's consider one loop, and the loop transfer function I'm taking H1 negative. Over here I'm taking G1, it's 1 and 1. This is the simple SFG. Now we'll see the terminology, right? First, node, it represents the system variables. So these are the nodes over here. These are the nodes. Okay. The second one is input node or source node. This node is the input node. Okay, so what is the definition of this? It has only outgoing branch. See, if this is the input node, it will have only outgoing branches. Okay. Next one is the output node or the sync node. The CS, this one is the output node. Correct. So it has only incoming branches. The output node will have only incoming branches. Is it clear to you? Let's come to the next one, and that is the path. Very important term. What is the path? See friends, it is the continuous traversal of the connected branches. These things are the branches. Okay. So what is the path? It is a continuous traversal of connected branches in the direction of the branch arrows. In this, see, arrows are given over here. For each and every branch, it shows the direction of branch. Okay. So the direction of the branch arrows such that no node is traversed more than once. This point is very important. Okay. Suppose you have to go from RS to CS. you can follow this path only, 1 G1 1, and you can reach to the output. Is it correct? So this is one of the paths given over here in this system, in this SFG. Okay, the same thing will see in this diagram also. Suppose I'm taking another loop over here in this direction, and the direction of this is not loop. Okay, this is the forward path. Now let's take it H2. Now if you want to reach to CS, you can follow this path and this path also, like this. You have two paths over here. So what you have to follow? You have to follow the direction of branch. Okay, now this point says no node is traversed more than once. What it means? Suppose you are starting your journey at this point RS, you are going to this side, then coming to H2, then you can't go to this way and you can't conclude your journey in this way, because if you'll do like this, you will consider this node 2 times and this node also 2 times. Okay, and we have to consider the single node only 1 time. Okay, now the next point is path gain. What is the path gain? Simple. If you are considering this path, so you have to multiply all these transfer functions. 1 into G1 into 1, it will be G1. So this is your path gain. Okay, product of branch gains in a particular path. Now let's come to the loop. Here it's loop, this one is loop. Okay, so what is the definition of it? The path which originates and terminates at the same node. It's starting at this node. Let's take it A. So this loop is starting at A and coming to A. Okay, so the path which originates and terminates at the same node and along which no other node is encountered more than once. Okay, this is again the same point. No node should be encountered more than one. Okay, now what is the loop gain? Simple, whatever loop you are taking. See over here, this loop consists by 2 branches. So the individual transfer function G1 and H1, we have to multiply them. So it will be G1 and H1. Though H1 is given in the negative, so we have to consider over here also. So this is the loop gain. Okay, now what is the self loop? The self loop consists by a single branch. At this node, suppose you have one loop like this. Suppose you have like this. So this I'll call the self loop. Only one branch. Okay. Now non-touching loops. What are the non-touching loops? Suppose at this point also, let me change the color of this. Suppose at A also you have one self loop like this. The direction of that is given like this. So this 2, this is L1 and this is L2. These 2 are non-touching loops. Okay, so what is the definition? If they do not share common node. If we'll talk about this L2 and L1, they are not sharing common node. Okay, they are far away from each other, so I can say these are the non-touching loops. If someone will talk about the non-touching loop gains, so what you will do, you will multiply the individual gains of these 2 loops. Okay, let's take this one is suppose H3 and this is H4. So non-touching loop gains will be H3 into H4. Correct? Now let's come to the Mason's gain formula. This one is very important because each and every block diagram problem or SFG problem for the gate we are going to solve by this formula only. Okay, so if any problem you get in the exam, you will convert into the SFG or block diagram, but you have to apply Mason's gain formula only. Okay, so what it indicates? The relationship between input and output of a SFG is given by the net gain between the input and output nodes is known as gain. So Mason gain formula is used to get the overall transfer function. Okay, you'll be given with complicated SFG diagram. Let me take one diagram over here for you. Okay, these are the nodes. You can number them 1, 2, 3, 4 and 5, right? Let's take, this is the loop minus h1. Let's take, this is 1, this is the transfer function of this, the system between 1 and 2. Let's take, this is g1, this one is g2 and this is g3, or take it 1 only, right? Here I'm considering this also. This is the path gain, I'm giving it g3. Okay, at this point I am considering one self loop minus h2 is the gain. This is one SFG I considered over here. So this is the complicated circuit. Here it will be input, here it will be output. And what is our task? What is the transfer function of the given SFG? So ultimately you have to do the C by R, you have to find out, right? So by which method we'll solve it? By the Mason's gain formula. Correct. So what is the Mason gain formula? So this is the formula, right? Where T is summation of k from 1 to k, pk del k divided by del. Okay. Now this T is the overall transfer function. Okay. Everything we are doing to calculate overall transfer function only. So this T is the overall transfer function or overall gain, you can say. What is this pk? This pk is the path gain of kth forward path. Kth forward path means there will be so many forward paths in one SFG diagram. There may be. That's why I am considering the summation from 1 to k. Here in the given SFG we have two forward paths. Okay, one is this. This is the forward path, means from input to output, and this is another forward path. So we have two forward paths. Okay, so this pk means the path gain of kth forward path. In this case the k is 2, so we'll be having two forward gains, right? What is this del k? First you need to understand what is del. So del is SFG determinant or characteristic function of the given diagram. Okay, so here we have seen two things. One is del k and one is del. So this del k is the system determinant related to this particular path. Means if you considered this first path, related to this path we will calculate the del k. If you consider the second path, so corresponding to the second path I'll get the value of del k or del 2. Okay. Now what is this del? This del is the overall determinant of the system. Okay, this is not associated with any path. This is the overall gain, and that is given by 1 minus sum of loop gains, individual loop gains. Okay, don't worry, just see it, because we'll do the problem, then it will be clear to you. Okay, so this is 1 minus sum of the loop gains. Okay, next one is the plus. Here the sign is plus, sum of gain products of all possible non-touching loops. In the first, if you want to calculate the determinant, 1 minus sum of loop gain. See, for this figure you have two loops, L1 and L2. So for this, if you want to find out del, so I'll do it over here. This is minus sum of loop gains, individual loop gains. What is the loop gain of this? Minus G1 H1, this loop G1 H1. So this is minus G1 H1. Perfectly fine. The second one is given minus H2. I have to add, means I have to take the summation. So this minus over here will be minus as it is. Is there any other loop, individual loops over here? No. So it will be over. Then plus, then you have to take the sum of gain products. Now we'll take the gain products because you are considering two non-touching loops and we'll add them. See over here you have two non-touching loop gains or two non-touching loops. So you have to take the product of loop gains. Here the product is minus H1 G1. Here is minus H2. You have to multiply them. So minus will become plus. You will get G1 H1 H2. Is there any other two non-touching loops? No. So this thing is over. Okay. So finally you will get 1 plus G1 H1 plus H2 plus G1 H1 and H2. This is your overall system determinant or characteristic function of the system. Okay friends. So this is the Mason gain formula. Now I'll tell you how to calculate the transfer function for this given SFG. Okay. So for this given graph, I have two paths. Let's take P1. So P1 is 1, G1, G2, and this is again 1. So this is G1 and G2, path 1. Okay. I have path 2. I'm taking it path 2, and that is 1, G3, 1. So this is G3 only. Okay. Now what about del 1 and this is del 2. Corresponding to P1 I have determinant function del 1. Corresponding to P2 I have determinant function del 2. So what is del 2? The definition is same. 1 minus sum of individual loops which are not associated with this. We'll see the associated with this path only. The loops which are associated with this path. See over here. This is the path like this. Then you will come over here, right? So 1 minus sum of individual loops, and if you are considering this path P1, so your loops should not be associated with this path, means should not be touching, I mean. If you are considering this path, you have only two loops in the system, L2 and L1, both are touching with this path. This L1 is touching at node 2 with this path. This L2 is touching at node 4 with this path. So I don't have anything over here. Is it okay? I have to consider the sum of individual loops which are non-touched with the path, given path. Is it okay? So over here it will be 0. What will be the value of del 2? Del 2 will be 1 minus, which one is the path? Sorry, this P1 is this path, right? The P1 is this path. So del 1 corresponding to this 1 minus, here I'll consider the loop gains which are not touching with this path, but in this case both are touching with this, so it's 0. Similarly for del 2 also it will be 0. Okay. And if you'll talk about the overall delta or del, it will be 1 minus sum of individual loop gains. It is minus H1 G1, this one, and this is minus H2 plus two non-touching loop gain products. It is G1 H1 H2. Is it okay? So it will be H1 G1 plus H2 plus G1 H1 H2. The calculation part is over. Now we'll keep all this value in this function. It will be T. Now what is the P1? P1 is G1 G2. So it's G1 G2. The value of del 1 is 1 over here. Let's take like this. Okay, plus. So this is the summation given over here. I'm considering plus. What is P2? P2 is G3 into 1. Divide by del, and del function you calculated 1 plus H1 G1 plus H2 plus G1 H1 H2. So this is your overall transfer function for the given SFG. Okay, so in this chapter we'll deal with this formula only. The transfer function calculation will be done by mesh and gain formula. Is it okay? So friend, this is all about to this class. In the next class we'll take only problems, no theory part. Okay, step by step I'll take the problems level. First I'll take easy problems, then it will be medium, and then I'll take the hard problems. Okay, we'll meet in the next. For the new updates you can subscribe LGF, and for the doubt solving you can find us on the Facebook. Okay, we'll meet in the next. Till then, take care and bye.